Welcome everybody. Today we'll be talking about the design of high-performance resonant micromirrors and their fabrication using the standard SOIMUMPS process. This research is financed by the Malta enterprise as part of the Eureka Penta project entitled Environmental Sensors for Air Quality. So my presentation, I will start by giving off a brief introduction. I will then go through the design of the microscanners that we're presenting. Next, I will present the design optimization scheme devised for both the direct drive and indirect drive microscanners. Following that, we'll go to the results and then some conclusions. Laser beam scanning is one of the technologies currently being considered for the development of miniaturized projection displays. Compared to liquid crystal on silicon and DLP technologies, laser beam scanning offers a focus-free image and offers greater potential for lower power consumption and smaller form factors. This is an example of a commercial laser projector smartphone currently on the market which uses this technology. However, this technology is not only limited to display technologies. Other examples include confocal microscopy, endoscopy, 3D scanning, spectroscopy, and LiDAR in UAVs and advanced driver assist systems. In order to develop a two-dimensional display using bidirectional raster scanning, we require two micromirrors, one offering quasi-static rotation to create the vertical scan lines, and another one for high-frequency rotation to create horizontal scan lines. So for horizontal scanning, the micromirror is operated at the torsional resonant mode to exploit the maximum transduction efficiency at resonance in order to achieve larger scan angles and higher scanning frequencies. The optical resolution of these resonant micromirrors depends on three main important parameters, which are the scanning frequency, the scan angle, and the dimensions of the reflective surface, that is, the mirror plate itself. Further improvement in these three parameters is limited in single-layer silicon devices by two main factors, which are the mirror surface non-planarity and air damping energy losses. Micromirrors operating at a torsional resonant frequency are subject to an inertial sinusoidal angular acceleration, which will in turn result in out-of-plane dynamic deformation. So if we take a perfectly flat mirror, here the resolution is limited only by diffraction and can only be improved by increasing the scan angle amplitude and its diameter. In the presence of high dynamic deformation, we have the formation of these wavefront aberrations, as we can see in the picture below. This results in reduced contrast between resolvable spots, leading to a reduction in resolution. In the case of air damping, our group has recently investigated in depth the accuracy and limitations of analytical and numerical air damping models for direct drive electrostatic microscanners. From this exercise, it is evident that the direct damping of millimeter-sized circular plates oscillating in out-of-plane rotation results in a non-constant quarter factor variation with scan angle amplitude. This can be seen in the figure below. This result has been verified from measurements, and in addition, recent publications have suggested the implementation of a nonlinear damping model for high amplitude oscillating micromirrors, as shown over here. The main research aim behind this study is to demonstrate that high-frequency scanning of a 1 mm diameter micromirror can be achieved while maintaining high energy transduction efficiency and dynamic flatness. The process selected for fabrication is the SOIMUMPS process offered by MEMSCAP. With this process, we have a cavity with a sufficient amount of depth underlying the device layer thickness as a result of the backside edge. This process also offers an additional metallization layer composed of gold and chrome, which is highly reflective and suitable for reflective surfaces. The downside of this process is the low silicon layer thickness and also the higher residual stresses as a result of the reflective layer deposition. These will offer additional challenges in the design optimization process. Two main microscanner actuation configurations were considered on the basis of electrostatic actuation via vertical comb structures, and these are the direct drive and the indirect drive configurations. The table on the left lists the target specifications for this design process. So here we can see the direct drive electrostatic actuation configuration. The mirror plate is suspended by an inner frame, which has been found from previous research to be the most suitable technique to reduce dynamic deformation in single silicon layer devices. The vertical comb structures are connected directly to this gimbal frame and mirror plate such that the rotational angle of these rotating comb fingers are equal to the angular displacement of the mirror plate. The second design concept considered is the indirect drive electrostatic actuation, where we introduce an outer frame. The vertical comb structures are directly connected to this outer frame, and by the concept of mechanical amplification, small oscillations of the outer frame result in an amplified oscillation of the mirror plate. The design process of both mirrors is divided in two main steps: optomechanical optimization and electrostatic fluidic optimization. In the case of the direct drive microscanner, the geometry is first parameterized according to the design input parameters laid out for optimization. We first perform a static structural analysis simulation in ANSYS, where we apply the process-related residual stresses to obtain the 3D static deformation profile of the mirror plate. This 3D static deformation profile is then fed into a model analysis, and from there we obtain the torsional resonant frequency and the modal separation, that is, this difference between the torsional resonant frequency and the adjacent bending resonant frequency. The torsional resonant frequency is then applied into an additional static structural simulation. Here we introduce the static equivalent inertial load or angular acceleration dependent on the torsional resonant frequency, and from there we obtain the dynamic mirror deformation and the torsional spring stresses, which are predicted for the maximum scan angle amplitude. In the second step, we perform electrostatic fluidic optimization. Here, the overall system damping was reduced by developing separate 3D transient Navier-Stokes models for the comb structure and the mirror plate. This work is performed using ANSYS Fluent. The figure of the left shows a typical model to analyze the damping moment on two halves of the comb fingers oscillating relative to static comb fingers. The figure of the right shows the micromirror, which is assumed to be rigid, which oscillates relative to the surrounding cavity wall boundaries. The main aim of this optimization step is to maximize the available electrostatic energy by performing combined electrostatic and transient CFD simulations. If we take a look at the static portion of this comb structure shown over here, as expected, a monotonic increase in the scan angle amplitude is achieved with increased number of comb fingers. However, if we consider the curved portion of this comb structure, at a certain distance from the rotational axis, no improvement in scanning efficiency is achieved with a further increase in the number of comb fingers. Next, we'll go over to the indirect drive microscanner. The first optimization step, compared to the previous microscanner, we include the amplification factor as an additional objective function. This amplification factor is defined in the out-of-phase torsional mode as the ratio of the angular displacement between the outer frame and the inner mirror plate. In order to perform electrostatic fluidic optimization of the indirect drive microscanner, an entirely different numerical model is required. While in the case of the direct drive microscanner, we could assume that the microscanner is rigid, oscillates in a rigid manner compared to the surrounding fluid. In this case, we have the outer frame which is oscillating at a completely different amplitude compared to the inner mirror plate. In this case, therefore, a fluid structural one-way coupled model was developed in ANSYS. Instantaneous displacement deduced from a finite element model of the oscillating structure is transferred to a CFD model of the fluid flow surrounding the same structure. This is done in order to update the boundary surface displacement of the dynamic mesh for each time step. And here we can see the results obtained from the fluid structural interaction model. Here we're plotting the pressure distribution on the moving structures, as well as the velocity streamlines along the midplane of the fluid domain. Now we'll move over to the results section. Here I will be discussing the simulated measured characteristics of the devices. When it comes to dynamic deformation, the final designs consist of a mirror plate suspended from a gimbal-type frame by 4 links. From simulations, it is found that the normalized dynamic deformation, which is defined in the equation below, is less than 0.1, and this is in line with the best published results for single-layer resonant microscanners. The figures on this slide demonstrate the effectiveness of gimbal-type support structures in reducing dynamic deformation. Here we can see that the majority of the dynamic bending strain is taken up by the frame surrounding the mirror plate. These results were also confirmed from laser Doppler Vibrometer measurements. A custom-built optical setup, shown in the figure on the left, was developed to measure the instantaneous scan angle using a position-sensitive detector. The figure on the right shows the nonlinear harmonic response of both scanners. We can see that the maximum response amplitude is achieved during frequency upsweep for both mirrors, and the indirect drive microscanner exhibits a wider operating bandwidth. Moreover, a constant overestimation of the torsional frequency is achieved from finite element model analysis. In order to measure the amplification factor in the case of the indirect drive microscanner, a novel method was proposed by directing a laser beam onto the outer frame to measure its harmonic response using the PSD. The figure on the right shows the harmonic response of both the mirror plate and outer frame. Given that we expect that the angular displacement of both the outer frame and the mirror plate is equal in mode 1, that serves as a good check to ensure that the harmonic response measured in the case of the outer frame makes sense. The amplification factor in mode 4, which is the intended mode of operation, is defined as the ratio of the peak amplitude response between the mirror plate and the outer frame. As we can see here, the good agreement is achieved in the amplification factor between the measurements and simulations. When it comes to wear damping, from simulations, it is found that the contribution of the cone structure oscillations towards the overall energy loss is greater than 30% in the case of the direct drive microscanner. However, in the case of the indirect drive microscanner, it is less than 5%. This shows that in the case of the latter indirect drive microscanner, the cone structure damping has negligible impact on the overall quality factor. The effectiveness of uncoupling the cone drive and mirror oscillations in reducing the overall quality factor is demonstrated in the optical measurement results, shown in the figure on the left. From these, the van der Poel nonlinear damping model parameters Q0 and QNL can be deduced as shown in the table on the right. So in conclusion, we have presented the design process of high-performance resonating microscanners based on advanced numerical models. Although the SOIMUMPS process is limited to a thickness of 25 micrometers, dynamic deformation and scanning efficiency on par with state-of-the-art in electrostatic microscanners can be achieved. Ultimately, the indirect drive microscanner design is suitable for projection display applications with SVGA resolution requirements, and the optimized gimbal frame design leads to an 80% reduction in the dynamic deformation of a circular mirror plate.